Welcome everybody to the NGI Technical Podcast. The NGI Technical Podcast is a medium where we communicate about expert topics from experts to experts. So it is about more or less in-depth geotechnical and engineering geological topics that NGI is concerned with. My name is Georg H and I'm the host for this episode, and I will be talking with my colleague from NGI, Tom Hansen. Tom will introduce himself briefly. For myself, I'm coming from Austria and I've been working at NGI for 2.5 years. My background was slowly transitioning from geology over to geotechnical engineering, where I've done a bachelor's and master's in engineering geology and a PhD in civil engineering. In my PhD work, I've been focusing on machine learning in geotechnics, where amongst other things, I've also been dealing with rock mass classification in a data-driven way. Aside from the PhD work, I've been working practically all my professional career long. I've been working in a company in Austria called Georg H, where I've been dealing with a lot of planning and very interesting construction projects in rock engineering, including, for example, the Semmering Base tunnel and the Brenner Base tunnel and things like that. And also here at NGI, I'm working practically with very interesting topics in Norway and abroad. But also I'm working as a researcher where I'm investigating geotechnical and engineering geological topics of all kinds related to ground modeling, uncertainty, machine learning, and these kinds of things. In the episode of this podcast today, we are going to talk about rock mass classification. And we are going to talk about this in the light of the first International Rock Mass Classification Conference that we are going to host at the end of October, so in about 2 months. The episode itself is not about the conference, but please be aware that there will be this conference, and there we will have many more in-depth discussions about rock mass classification, rock mass characterization, and also things like digitalization in rock engineering. Be aware that the episode starts gently into rock engineering and rock mass classification, but we are going to get a bit into the more nitty-gritty details and also a bit more sophisticated talk about digital topics like unsupervised machine learning. But don't shy away from that, because first of all, I would say this is the future of rock engineering. And second of all, you can find links in the show notes to all the papers that we are mentioning during the episode. So we try to say in the episode when we are actually talking about a paper of ours, but if we don't, please still look for the paper in the show notes. All the links are given there. Lastly, before we get into the episode, I want to say that all opinions expressed are the ones from Tom and myself. So it is our opinions and not necessarily the opinions of NGI. This is important to say because rock mass classification is a somewhat of an emotional topic sometimes. People feel passionate about their classification systems, and people are also subjective in a way that they are biased because of where they come from, the experiences they have made, and how different systems have been performing in their own experience. And this same is of course true for Tom and me. So please, when you listen to the episode, see it in that way, and please also do not shy away from getting in touch with us about anything that we express in the episode. Enjoy. And we're on air.
That's good.
Okay, yeah. So welcome, Tom. And could you please introduce yourself briefly? Give us an overview over your technical career and your academic work, and just describe what you're doing.
Thanks, Georg. So I started my study days at NTNU in Trondheim. I have a master's degree in technical geoscience. So it's basically tunneling and mining and so on. I started my first work at Spitsbergen in mining, coal mining, for Store Norske Spitsbergen Grube Company. Worked with mine planning and rock support and everything cool in rock mechanics. Then stayed there for 5 years, went on to the next 10 years in railway construction. Actually, for Bane NOR, the big Norwegian client for railway construction, and worked on several intercity railway projects, basically tunneling and rock-related projects. both as a phase engineer, doing rock mass classification and all these practical things we will discuss today, and also a construction manager and project manager, so also kind of a little bit into the contract regimes and the economics and how these kind of interconnect in big rock projects. Then the last part, I made a shift in my career, moved to NGI 5 years ago and started a PhD together with the University of Oslo. So I used, the last 4 years, I've used 75% of my time on the PhD in the research group for artificial intelligence and robotics at the Informatics Institute, where my working title of the PhD is decision making in underground construction with machine learning. I'm about to deliver that soon, so we'll see. I think I have some high hopes for kind of using machine learning to at least solve some of the more subjective stuff in rock mass classification and other problems in our industry.
Yeah, for sure. So I think you have probably seen a lot of these subjective stories or experiences in your career. What was the motivation for you to go from the practical work to the PhD? Because most people who do a PhD do this early in their career and then they shift over to practical work, but you went the other way around.
Yeah, so from the start, I think I really wanted to go out directly after the master study and to do something, to kind of feel the rock, as we often discuss a lot in study days in our field, how important it is to kind of touch the rock and see a lot of rock faces and sites and problems, to be aware of what is the reality out there. But then with the years, I've seen a lot of stuff where I think we have possibilities to improve the way we do it. And it's basically connected to so much we do today is very subjective. It's in a sense not so scientific. It's very much design as you go in a lot of our rock projects today, and it's empirically based. And if you kind of send 5 engineers to the site, you will get 5 different answers. Yeah, and I really felt that this is not the optimum way to do it. At the same time, I remember working at one of the big intercity projects, on tunneling projects, and I started to see machine learning back in 2012, 2013, appearing as a new discipline or new domain. Then you had a kind of a starting of deep learning and really making some big breakthroughs in AI, also in fields like biology, physics, and so on. And I thought that this could be something that could be useful for our very subjective and empirically based science. So I was really motivated then to kind of, this must be a tool that we can apply for at least some of our problems. Yeah.
That's really interesting, and I think also very valuable to bring practical experience into the PhD. Before we dive really deep into the subjectiveness and also generally about rock mass classification, perhaps let's start with the very basic things. What is rock mass, and these kinds of things. We don't have to be too detailed about definitions, but many of the NGI technical listeners have more of a soil mechanics background, or perhaps are not that deep into rock engineering. So what's the difference? What would you say is the difference between rock and rock mass, and what are the challenges that we face there?
Yeah, I mean rock, we have this ISO standards that define rock as a natural occurring assemblage or aggregate of mineral grains, also a combination of mineral grains and crystals into a compound which we call the rock. So it's kind of a class in the same as we have in classification system. It's a combination of minerals and grains, and and particles into a rock. A rock mass, on the other hand, is this intact material together with the discontinuities and weathering zones or weakness zones in the intact material.
Yeah. So the discontinuities, I think this is perhaps the most prominent or most striking difference between rock mass and soil as an underground material, because I would say in soil we usually have a very dominant continuity of the ground and the ground properties, where it's a mixture of particles of different sizes and so on. But in rocks we have the discontinuities, and these can be fault zones on a big scale, these can be joints, these can be other kinds of fractures, but we have distinct parts of rock that are separated from other parts of rock with discontinuities. And that, of course, that's a big challenge.
Yeah, and that makes the whole material very, very anisotropic. That's so normal. And you kind of, in different directions, you have totally different behavioral of the material. That's, of course, a challenge, and makes it much more challenging to engineer constructions in this material compared to soil and of course steel and concrete and these very easy materials.
For sure. I mean, I think we should be a bit careful. So of course engineering in soil is not trivial. We don't want to anger anybody, but I agree that the challenge in rock masses, and especially the very challenging rock masses, I think it's the anisotropic ones, it's the ones with very complex discontinuity intersections and these kinds of things. If we then go on to rock mass classification, so we have the rock mass as this complex geomaterial, and for engineers started decades ago, in fact they started basically centuries ago, to try to classify these geomaterials in certain ways. Why do you think that is? Why is there this? Why have engineers always tried to come up with classifications of these rock masses?
I think that's very related to what we discussed just now. That this material is not homogenic at all. It's so heterogeneous, and we need some way to kind of simplify the material in order to design or construct our constructions in this material, to find a way that is kind of comparable, perhaps, to other more homogenic and known materials. I think that's kind of the main motivation, to find something comparable, so we can, as engineers, kind of can operate as engineers in a way.
Yeah, I agree. I think the realization that this geological material is very complex in nature, and the need to still do something with it is perhaps one of the biggest motivations to actually invent something like rock mass classification. We have a paper here. So I think one of the oldest sources, a very renowned publication, of course, from Bieniawski in 1973, is titled "Engineering Classification of Jointed Rock Masses." Bieniawski is there also the father of the so-called rock mass ratings, the rock mass rating, one of the most prominent systems up until today. And Bieniawski defined the purpose and requirements of rock mass classifications, that a rock mass classification, it should divide the rock mass into groups of similar behavior, as you said. So this is the first requirement that he said. But I think this is there is an interesting aspect. So far we talked about rock mass, but here he's talking about rock mass behavior or groups of similar behavior. So, and I think this thinking around rock mass versus rock mass behavior, that's something that is not very apparent in the first view. So how would you say, what's the difference between rock mass and rock mass behavior?
I think that when you include behavior, then you include forces acting on the rock mass. It's the water pressure, it's rock stresses and so on that very much kind of give a signature on the rock mass, how it behaves when you build your construction. And of course, I think that could lead to some confusions in in our domain as well, that you have this very defined rock mass. On the other hand, you have the forces acting on the rock mass. These are kind of two, of course, connected entities, but at the same time they could be divided. And some people think about the rock mass, some people think about this combination, and it's not often that, or it's a lot of problems or a lot of occasions where they are kind of mixed and confused a little bit, I think.
Absolutely, and I think also a big challenge is that the rock mass, it's kind of always the same. If you look at the rock mass in one place, then this is the same no matter how you observe it, up to the extent that you can actually observe it. But the rock mass behavior for one rock mass can be quite different. So if you have the same rock mass and let's say you drill out the drill core, then the observable behavior is based on the, as you say, on the forces that you actually put into the rock mass. So your core will look in one way. But if you excavate the rock mass then with drill and blast tunneling, it will present itself, it will behave in another way. And if you excavate it with a TBM, it will also behave in another way. And if you excavate it from different directions, you will also see different behaviors. So that's, of course, quite a big challenge. And especially for classification systems, I think that's really tough to incorporate this complexity and this interaction between rock mass and the rock mass behavior. So depending on the actual engineering endeavor that we do, right?
Yeah, and I think that has also been one of the main discussions in the world when they compare different systems, how they make use of the forces, which kind of parameters do the different systems use to kind of to implement forces. And I think that's one of the core points of the debates going on when we discuss the differences between rock mass classification systems and so on.
Yeah, absolutely. Yeah. If we go on with this, so what Bieniawski further describes, so the first requirement for a rock mass classification is that it should divide the rock mass into groups of similar behavior. But the second is that he describes it should provide a good basis for understanding the characteristics of the rock mass. I think we discussed this quite a bit now. And there, of course, he mentions that the characteristics of the rock mass, so I would say this includes things like the intact rock strength, the discontinuity properties, so the surfaces of the discontinuities, the density of the discontinuities and these kinds of things. So this should be included in one way or another. And then in number 3, he says to facilitate the planning and the design of structures in rock by yielding quantitative data required for the solution of real engineering problems. And I think that's an interesting point, because there the systems start to diverge quite a bit, because some systems are very much focused on to specific engineering applications, while others are more general. How is it in your experience, especially in Norway? What would you say are dominating systems or very widely used systems, and what are their focus points?
Yeah, I mean, naturally, it is the Q system that is the most used system in Norway. It has been developed in Norway from a lot of people at NGI. And that is by far the most used system in Norway, at least in underground construction. Regarding rock slopes and rock cuttings, it's not. I don't think that so many systems are in use. It's more a qualitative assessment in rock slopes and rock cuttings.
Yeah.
But of course, then for ground investigation again, it's very often we classify the Q values along also other joint frequency and other kind of easier to recognize values.
Yeah. So for the listeners, we are going to put a link to the Q system handbook into the show notes of the podcast. But to you, Tom, the question would be, so I also see this a lot in Norwegian, especially in tunnel construction. The Q system is a very prominent one. How was this in your mining days? How did you deal with rock mass classification and characterization back then?
And that's a very interesting question, actually, because in mining in Store Norskes coal mines, it was no use of rock mass classification systems. Because we used much more a combination of measurement, a little bit closer to NATM perhaps, monitoring, constant monitoring of the rollways in the mines, and we acted with remedial support when the monitoring extended some kind of limit. That was more of the classic way, and we also instrumented bolts and different kind of rock support to measure forces, because in a mine, as you know, we have the kind of this dance of rock stresses around in the mine when the mining entities like long wall panels or room or pillar systems are kind of moving close to a roadway. You have a big redistribution of stresses, and you have movement and cracking and sounds in the rock all the time. And then you also need to measure and have constant monitoring of the rock mass in order to follow the stability of the roadways. Maybe you need to seal off a roadway, or you need some extra support and so on. And that's the way we did it. We had a big system of monitoring in the mines to follow the rock support. And also to design the rock support system. How many bolts we should use, how long should the bolt be in different kind of rock types. Some places we had sandstone, some places we had kind of a cake of shale and silt and sandstone and everything. Just to find the right length of bolts, we used a lot of monitoring and instrumentation.
But you made all of these support design decisions, or largely based on the observations that you actually made, and not on some predefined systems or anything like that.
We also combined it with numerical modeling. And back calculated from the measurements.
That's really interesting.
And then it was really interesting to then move over to the tunneling industry in Norway. And see the kind of big difference from my mining days to the tunneling industry in Norway, or maybe we can say in Scandinavia, but it's much less monitoring. And I tried a little bit to push monitoring and instrumented bolts and so on into the tunneling industry, but I think that was hard. It's kind of not so close to the culture in Scandinavia. I'm using that kind of approach to tunneling design. Could be back because rock mass classification was more adopted and as a design method in a way, combined with the observational method, of course.
I mean, it's the use of the Q system in Norway. What definitely is fair to say that its success in Norway justifies its use to a certain extent. So it works, and that's undeniable. Tens and hundreds of kilometers of tunnel have been built in Norway using the Q system, and basically one can say it does the job.
Yes, definitely.
But I mean, what you say, you also mentioned the NATM, so the new Austrian tunneling method. This is a tunnel design method, let's say, that comes from Austria, as the name says. It's not that new actually. It's new since the 1950s. But there a different approach towards rock mass classification is used. So in contrast to, for example, the Q system, the NATM is based on the idea that every rock mass is unique, and every rock mass gets its own rock mass types. So you do investigations, and then you define rock mass types based on homogeneous volumes of ground where you think that they are going to have similar ground properties. And then based on that, you define ground behavior types, and based on the ground behavior types, you define system behavior types. So the system behavior is then the interaction of the ground with the actual structure that you're going to build, and you verify everything then with support, with monitoring, and also on-site observations. So it's interesting to see that. I think what you described from the mining is quite close to that, actually.
I believe so, actually. And we were very connected to the mining industry in UK, Australia, US, And we discuss closely with academics and consultants in these countries, especially a lot of miners from UK mines at the time, at least in the 90s, and it was a lot of mines still in UK, and they had big rock mechanics divisions, and we discussed these systems and approaches with people from these three mining countries.
Yeah, interesting. The last of the 4 points that Wieniawski in his paper that is now 51 years old makes is that rock mass classification systems, they should provide a common basis for effective communication among all persons concerned with a geomechanics problem. And of course, that's also an important point, because I also notice in my own, not that extensive, but still existing construction site experience, that communication is one of the main challenges, that you have people from all different disciplines on site and they need to talk with each other. Not everybody can know the ground as well as a geologist, but at the same time also the geologists have to be able to connect the ground to some kind of support and design. So communication is important, and therefore, let's say very sophisticated systems, they might suffer from this problem, because of course communication is easier the easier your classification system is. Do you have some thoughts on that if you think about different rock mass classification systems?
I think that it will be difficult to use a system or to communicate the values if it's not too easy to make input values and do the classification for the system in the same way. If it's easy kind of to do it in different ways, so you can, for instance, have the same class for different input values, so it's not kind of deterministic in a way. Then you can deal with the totally different problems but have the same values. So we communicate the same class, the same values, but in reality you discuss totally different problems. That could be a challenge for systems like that, and we see that in some of the systems in use today. And that makes it harder, of course, to communicate across different contract regimes and tunneling cultures or mining cultures around the world. It would be very nice to then communicate the same thing.
Absolutely. I think that problem is also one of the main issues that people raise against systems like the Q system or also RMR and these systems, that they put one single number on the complexity of the rock mass, and ultimately you can get the same Q value with a lot of different rock mass behaviors.
Yeah.
And of course that makes it then tricky, because you need to act differently with respect to different rock mass behaviors. But if everything is subsumized under the same number, then this is a bit of a questionable decision basis sometimes.
At the same time, I just want to mention that this could work very good if you are kind of in a close context.
Yeah.
If you are in your tunneling world, maybe these 2-3 projects at the same area, in the same contractor or the same client, this is where you are geologically. Then it can make sense to kind of compare values.
Yeah, that's absolutely true. What we do see also, of course, is that this high level of uniqueness, so having dedicated systems for every single construction site, comes along with its own challenges. When it, as you say, comes to comparability, it becomes very, very difficult to compare one tunnel with another tunnel if your rock mass types and your system behavior types and these kinds of things are completely different. Yeah, for sure.
And then it's just a reminder, and maybe it's a bit of a kind of digression, but when it's a big debate going on, what's the kind of the best tunneling way, or the best way to do tunneling in the world? And when you don't compare the same thing, of course, then it's very hard to compare different methods with different contract regimes, different machines, and actually also the values come from different rock masses and different entities. It's really hard to kind of say that this is the best method for tunneling in the world. Yeah,
Absolutely. It's as in many other aspects of life, of course, comparing one tunnel to another tunnel is almost never possible because of so many things that are also not related just to the technical aspect. So that's a challenging thing. One study that we have done in the past years, you've also been involved, so there I've been in the lead, was that we investigated the international distribution of rock mass classification systems. And I guess several of the listeners perhaps have even participated in that survey. So what we have done is we made a survey with Microsoft Forms, and we send out questions to rock mechanics experts about which rock mass classification system have they used in a particular country for a specific application like tunneling, slope engineering, and so on and so forth. And first of all, what was really interesting for me was to see the extreme wealth of rock mass classification systems that we have today. I think we started in the study with around 20 systems or something like that we have had on our radar. So it was you, it was me, it was some other people that were involved. And we ended up with a total of 37 rock mass classification systems that were then also suggested to us. So, and as a result of that, we produced also a family tree of rock mass classification systems that goes very far back from today's perspective. I mean, things like the RQD from Deary in 1963, that was very influential. But we see this ever-growing tree of rock mass classification systems that becomes bigger and bigger. Why do you think that is? Why do we see such a? I mean, it's on the one hand, it's interesting to look at it from a tree-growing perspective, but it also shows that the community has not narrowed down on one specific system or on one specific way that actually works best. Why do you think that is?
I think a part of the reason is that from the start there has been a discussion that this and this system, they don't adapt good enough to my special rock mass conditions, to the way I see the rock in my country or my tunneling culture, and I need to develop or further develop the system and try to kind of close some of these problems, maybe to add a new feature and to add some new experimental data, empirical data, to kind of adapt the system to your special use case. And maybe to add something about failure systems, to add something more about water leakage and so on, that better kind of fit to my problem and my industry and my sub-industry. And then you have this growing tree in all directions. I also believe that what I mentioned earlier about different contractual regimes and different machine logistics and so on will affect how we use the systems and for what purpose, and maybe then have a kind of an incentive to change them a little bit in different directions.
Yeah. I would also suspect that increasing specialization is related to this proliferation of rock mass classification systems. It's also interesting to see, for example, that the very early systems, they had more of a, let's say, a general tone to them. So they have not been aiming at single specific applications. Whereas what we see in the last years, more and more systems, they are focusing on, for example, slopes in coal mines. So very specific applications. But what is interesting, or what I personally find interesting, I also deal a little bit with constitutive models and also soil mechanics. And in constitutive modeling, we can see quite well that the more sophisticated the models become, also the input becomes more and more sophisticated, which is a challenge by itself, because to calibrate a constitutive model, you need to calibrate more and more and more parameters. The parameters get increasingly difficult to assess. But we don't see this for rock mass classification systems. So even the ones that came out in the last decade, they sometimes even very prominently say that they do not need many input parameters. They are stating quite explicitly that everything that goes into the system can be estimated. Why do you think we do not really see a increase in the let's say the level of detail how we actually observe and measure the rock mass?
I think it's mainly caused by the way the systems are used. These are mainly thought about or used as a kind of a rule of thumb systems. You need them in design as a go approach often. Often they are used like that in mining and tunneling. And they cannot be very complicated. What are actually the input values you are able to kind of easy collect on the face or in the mine in the short notice? Then you need kind of easy to extract, easy values, and have a kind of a rough idea of what to do next.
Yeah,
I think that's what is at least one of the main reasons.
I would also guess that this is the background, but do you think that this brings us forward? Quite bluntly said.
Of course, that's. I'm not sure about that. Of course, that involves a lot of subjective decision making. Back to my motivation for going into machine learning and informatics and kind of blend these two worlds in a way, or at least try to put a little bit more science, but then at the same time be very aware of not introducing very complicated methods that just makes the whole process slower. We don't need to slow down mining or tunneling. We want to make it faster and more efficient, and then to find the ways to classify, because we still need to classify this very heterogeneous material, but we should use other ways to do that than this very subjectively based systems. So I'm not sure. I know we will go into more data-driven systems.
Yeah.
So you can perhaps bring up the topic later on, but in that direction, of course, is what I believe is the one of the directions to go.
I agree. What I also, and I mean, this is my personal opinion more, what I would think is that the reason why we see this continuous increase in the number of rock mass classification systems, that essentially many new systems are very, very similar to the old ones. Not in a way that, I mean, they are more specialized, but in the way that they work, and also in the way that these models produce outputs. This is essentially the same as it was before. And the newest systems, they collect the same number of inputs than the oldest systems. All the inputs are subjectively assessed like in the oldest systems, and so on and so forth. And I think as long as we don't have more like, let's say, a bit of a paradigm shift, that the community is not open to move towards new technology, we will see more and more systems, because they essentially don't really solve old problems. But perhaps this is, it is my assessment of the situation, I would say. Yeah.
As you know, I agree more or less to your opinion there, and we have done quite some work in this direction. So
Speaking of digitalization and these topics, I want to talk a bit about one of your current papers. So you are currently working on a paper about also rock mass classification. That is also one of your PhD papers, and I think this presents a very, very interesting and let's say. It presents an approach that is on the one hand sophisticated, but on the other hand also it can be perfectly integrated into everyday operation at the tunnel construction site. Could you, you know what I talk about, so could you elaborate on that a bit, please?
Yeah, I can. And first a quick background on this, because I've been thinking and working on this problem for quite some years. And I always wanted to find kind of a data set that is much more objective, and also to that give us information outside the rock surface, what we actually want to support, or where we actually want to insert advanced support, or we can use it for our blasting system and so on. And then we need information outside the rock surface. And of course, for a long time, there has been geophysical data sets. It's a lot of noise in these systems. It's a bit involved in how to collect the data. Back to my principle of not interfering more than necessary to the tunneling or the mining. You don't need to slow down the process. So you need to find a data set that you can run it on the phase when you do the operation and don't stop the factory, the factory approach to production, tunneling and mining. And then, at least in Scandinavian countries, we have for, 10 years, we have collected the measure while drilling data. So most rigs operating in Scandinavian countries, they collect measure while drilling data autonomously or automatically. It's just collected, so it's a very cheap way of collecting sensor data. And what we do then is, in measure while drilling data, you collect the information about the rotation, the penetration, the torque, and feeder pressure and so on. A lot of values that potentially should say something about the rock mass, because you're kind of touching the rock.
But is this only done in exploratory drillings, or is this data collected all the time?
They are collected from all drilling. So when you drill a bolt hole, a hole for blasting, exploratory holes for grouting, every hole you drill, you collect this data. And then, of course, you have data at the same distance around the surface as you have drilled. So if you drill a 30-meter long exploratory holes, then you have information 30 meters ahead of you.
Yeah, okay. And what do you do then with this data?
And of course, for a while or for many years, it has been challenging to interpret this data to kind of actionable decision making. We have calibrated, we have cleaned the noise and so on for many years, and visualized this data also in BIM models and 3D models and also 2D plots to show in different colors what you can expect when you enter this area. But still it's not very clear. You still need to interpret it as an engineer, and what do I actually need to do now? Should I install spiling bolts? Should I blast 1 meter instead of 5 meter? It's kind of hard to make that decision, because it still is a kind of a very noisy but yet colorful image ahead of you, but it's noisy and it's hard to make that final decision. So you need a way to kind of transform or translate this information to what you actually need to decide.
Okay.
And then enter the world of machine learning. That, just first to say that machine learning is definitely not for everything, but for some problems, this could be a very nice tool to find information in big data sets with lots of noise and very much information, but you need to kind of find what you actually is important for you.
Yeah, okay. So I see that natural data, measurement while drilling data is a very rich data source here in Scandinavia, and of course it's, as you say, it produces nice colorful images, but also making something out of these images is quite a challenge. What kind of, or can you elaborate a bit on machine learning in general and what kind of machine learning you use? Because I think for many of the listeners, this is a very exotic topic.
Yeah, so machine learning is basically to replace a kind of a logic programming method, which we have had until machine learning, where you say that if that happens, you do this, if that happens, you do this, and so on. But if the information or the data you are looking at is very complicated, you need thousands of nested loops of logics to actually account for all this, ifs and else. With machine learning, you'd find patterns in the dataset, in your empirical dataset of input and output values, and relate these and then make a program itself by training or running an algorithm on this. This could be as simple as a linear regression, as we know about linear regression, to find pattern in between an input value and an output value. We can have multilinear regression, it's just more variables. And then actually machine learning is just variations of these algorithms to find this pattern from input to output, to map the input to output, that's a classic way of thinking about machine learning, and we call this approach supervised learning because it's supervised by the labels, the output values you have linked to your data set.
Yeah.
So let's say, just to follow the system of rock mass classification, you can have this input data set of measure wire drilling data, and you can have a rock type as a label for the same section of a tunnel. But that's a supervised way of training a machine learning model.
But in this case, the labels, so the rock types or the Q classes or whatever, they are coming from humans. So they are coming from geotechnicians or engineering geologists going into the tunnel, making an assessment. And then after this has been done, you do the training from measurement while drilling data to the labels that they acquired. But what you present in the paper, this is unsupervised learning. So supervised learning, I mean, this is, let's say, even today, this is fancy enough. But why do you not use supervised learning here?
And that is basically related to what you just said about the labels. The labels we have in rock engineering and also in soil engineering and geotechnical engineering in general. The label is very subjective and is not a perfect ground truth. It's very hard to say what is the ground truth here. Is this the right Q value? Or is this the right rock type? Is this the mineral type? It's very hard to say. It normally involves various degrees of subjectiveness.
Yeah,
and some could be easy. It could be easy to measure the uniaxial compressive strength of the rock. Okay, that is a way to do. Could be a way to do it, to have a more standardized label. On the other hand, to kind of predict UCS, maybe doesn't tell us so much about the actual action to make in the end.
Yeah.
So you need to find that label in supervised learning, which is a good mapping to your data set and is a good label. And to find a good label in rock engineering is very hard.
Yeah, exactly. So I think a comparison where this works very well in general is that, for example, in supervised machine learning, there is a very prominent data set. This is the so-called MNIST data set. It consists of handwritten digits, so numbers from 0 to 9. And ultimately there, the input-output relationship is very clear. You have the handwritten number, and then you have the label, the actual numerical value of that number. And there, the ground truth is perfect. The person who writes the number is also aware of what the actual label should be. So there, the output, you can really go for 100% accuracy. But in rock engineering, of course, the problem is then the ground truth is no ground truth. It's not the truth in the sense that this is the reality. It is what has been observed by one single person on site. So that, of course, makes supervised learning generally difficult to apply to many rock engineering problems, I think, or in general geotechnical problems.
Yeah, absolutely. I think supervised learning, it's a lot of supervised learning papers and studies out there. I think several of them are kind of questionable when you have this label. What do they actually show? And it's in general hard to do supervised learning for several problems in our field, I think.
Yeah.
And I've done it myself. I tested this. I have one paper at least on this, and I see really the challenges of doing this.
Absolutely. So now what exactly is unsupervised learning, and how is it different to that?
So unsupervised learning is mainly is kind of two groups of unsupervised learning that are more familiar to people. First, of course, is that you have no label. You have only the data. So it's about using this data to find the patterns in the data. One unsupervised learning technique is to do dimension reduction. If you have a very big data set, or let's say for DNA or also for measure wire drilling data, we have very many data points for the same location. To be able to feed it into an algorithm in a computationally efficient way, we need to reduce the data set. Otherwise, you will get too much noise and it's just too hard to run it. So you need to reduce it down to an representation that is not so far away from the actual representation.
Yeah.
And very classic approach is principal component analysis. It's kind of classic in statistics to reduce in a linear way the data sets. So that's one type of unsupervised learning. The other way that most people think about is to do clustering. To cluster samples with some way of the same features into clusters or groups of similar like material, if it's a material you have data about. And that's what I've done in the paper I'm working on now, which is out on archive as a preprint, where I cluster measure by drilling data or kind of samples of about 50 values. It's a tabular sample of 50 values of measure by drilling data, where I first dimension reduced it from when you do collect measure by drilling data, you collect maybe one value for every 1 or 2 centimeter. And if you then drill 120 holes for a blasting round, that quickly adds up to thousands of values.
Yeah.
So to get down to these 50 values, I just computed statistical values like mean and median and standard deviation and so on. And from this, I have 50 values for the different feature values in measure by drilling. So the rotation pressure, the penetration, and so on, and median and mean and so on for these features. So then I have this 50 value vector, and then I run a clustering algorithm on this. A clustering algorithm that has been around for quite a while is k-means. Is also quite a simple and mathematically simple method, but it tries to find compare all these tabular samples to each other and try to find the ones that are kind of close to each other in different ways, using some kind of a distance metric to compare each row of data. In the last years, we have got much more sophisticated clustering algorithms that do the job much better. Of course, k-means can work for some problems, but lately, in the last 5-6 years, we have had more sophisticated clustering algorithms. And I can just mention one is that is kind of the state of the art at the moment, is often regarded as state of the art is the HDB scan, which I've used to cluster measure by drilling data to material or clusters of the same material type.
Yeah.
I then used my existing labels of a rock type, if it's a granite, or it's a rhomb porphyric rock, or if it's a shale or a limestone, and colored the clusters with the rock type I already had. And what I realized that actually these rock type values almost align perfectly with my clusters. So that's tell me something about the kind of the physical meaning of the clusters. I'm still early on in investigating what's the properties of each cluster. But then in an unsupervised way, you find a system in the rock mass material from this measure by drilling data, which is an objective data collection method done automatically, almost without no cost.
Yeah.
And find systems in the rock mass material, and you are able then to kind of design new classification systems around that could be targeted in different directions depending on what your problem is. Is it rock mass stability risk? Is it blast stability? Is it grouting effort?
Yeah.
You can kind of tune this signature from the measure by drilling data, which appears to be a good signature of the rock mass in your direction, or in direction of your problem. At least that's how it seems to be, or seems to work at the moment. Yeah.
I find this very interesting because I've played around with approaches like that for a while now, and perhaps to summarize, so the approach is that you take your measurement while drilling data, which is 50 dimensions, you said in this case, you reduce the dimensionality, and then you apply clustering algorithms on these dimensionality reduced data set, right?
Yeah, so it's kind of a condensed information from the dimension reduction. Yeah.
So perhaps just to elaborate a little bit on the dimensionality reduction technique, because I remember when I got into this topic, this felt very odd for me. I think a nice way of describing dimensionality reduction is that, so for the listeners, if you think about different people, for example, Tom and me, we share a lot of different properties, but we also are dissimilar in different ways. So, for example, we are both engineering geologists, but we have different ages. We are both men, but we live in different places, and so on and so forth. And these 50 dimensions that Tom is speaking about, this can be properties like that, but just based on MVD data. And the problem is that we as humans, we always struggle with very high dimensional data. So I would say that everything beyond 3 dimensions is a challenge for most people. And then, of course, if you have 50 dimensions where each dimension may or may not have very interesting information, then you have to do something about that. And if you reduce such a high dimensional data set, you can imagine the output as a map. It's always nice to really look at the dimensionality reduced data set, where you end up with a map where you have densities, or you have different, basically, let's say, islands of data points in different parts of your map. And these data points, they start to appear in areas where they share common properties. So what I think, please correct me when I'm wrong, but basically what you're doing with the MVD data is that you are, let's say, you're eliciting the original structure within the data out of this data set with this dimensionality reduction approach, right?
Yeah, I try to use that to kind of condense the information to something that is easier to cluster or to find similarities between. Again, it's about removing noise to find what's the actual meat here.
Yeah.
And then it's one technique I haven't mentioned yet, but it's a comparable technique to principal component analysis for dimension reduction. So before I input this 50 value sample into a clustering algorithm, I used a dimension reduction technique called UMAP. So it's a manifold learning technique. I won't go into the details. No. It's quite complicated.
That's for another podcast.
Yeah, but it's that is also kind of a state of the art. So this combination of UMAP plus HDB scan for clustering, that's kind of the state of the art for very hard problems in, let's say, in biology and earth engineering systems and so on.
Yeah,
to find new classes or group data in new ways based on very high dimensional complicated data.
Yeah, I think this is a very nice approach because it's fundamentally different to how rock mass classification has been defined so far, because here you really present a way of doing this in a data-driven way without imposing classes onto a data set, but rather learning the classes from the data set. And I really like that. How for this specific application, because I mean, still it's very nice. It's a very promising approach, I think, but it's also, it's mainly related to tunneling in Scandinavia. So the field of application is a bit narrow, let's say. How could we scale this up?
I mean, the technique is very general. It's to use measurable drilling data, and we can have measurable drilling data every time we drill in rock. It's just about collecting this data. They are the same all over the world. So we can basically use this every time we have rock and drill in rock. Then we can use the same technique.
Yeah,
and tune these systems in different direction. Because as I said, we can have this core of a rock mass description from measurable drilling data, but then you can add, it could be pore pressure measurement, it could be the kind of the overburden height, and so on, to kind of tune your new classification system to your use case, using your domain knowledge as an engineer.
Absolutely. I mean, that's nice, but I still think practically speaking, measurement while drilling data acquisition has a very, very high standard here in Scandinavia. And a prerequisite for applying this is, of course, to have the same quality of data in other places as well. But I agree, this could be one way forward, absolutely.
Of course, you need to have the system set up. The sensors should be on the rigs. You need pre-processing techniques and so on. So that, of course, there are some kind of background system that you need to have in place before you can use it. That's true for sure.
Okay, yeah. I think we've come quite a long way with rock mass classification from the first days from Wieniawski in 1973. I mean, this was not the first days, but still it's a couple of decades old now, up to unsupervised machine learning for developing new rock mass classification systems. I want to end up with 3 questions. So my first question is, where do you see rock mass classification in 10 years? Where do you see it in 100 years? And where do you see it in 1,000 years?
It's a very big difference between these perspectives. But let's say for 10 years, I mean, we are quite conservative industry. So I think things take time to development. We see now some early papers and describing more data-driven systems. I believe we will see that deployed in 10 years from now, much more data-driven systems. Still, it will be, of course, the human that make the final decision. These are decision support systems, but they are made in a data-driven way, much more objectively for the engineer to use the information. And I believe we will see these systems wherever we can collect the data, because data is the source and actually the most important thing here. We need to have that in place. And then back again to, we see that very much is in place in Scandinavia. Let's hope it's more common in other parts of the world in 10 years. I believe it will be, because it's actually quite cheap to collect this data.
Yeah.
So yeah, that now we have just talked about measured by drilling data. Of course, we can see the development in, especially I believe in geophysics. If we see a steady development in geophysics to make this simpler and simpler and easier to do from phase in operation in the cycle. But we also need to interpret these data in the same way, in a quick way, in a data-driven way. But I believe we will have much more of this in 10 years, both in drill and blast and TBM tunneling. That was 10 years.
Now it gets more tricky.
For 100 years, 100 years is a long time. I believe that, okay, this, if we discuss the use of the systems, I think the phase engineers are not underground in 100 years from now. These are more of the safety critical jobs we do today, to be on phase, to be present on phase. And I think we will see that is not we do not make optimal decisions as humans, because we need to do this fast. It's hazardous environment, it's dark, and to do this quick, to kind of process all this information in a quick time, we will realize that machines and computers can do this better than us in 100 years from now. And of course, then we need to have better collection techniques and redundant systems and very good safety in the operating systems. But I believe in 100 years we will have that. And then we will have no or very little people underground, I think.
Yeah, I agree. I also think that increasing automation and digitization will go along in the next, with the whole engineering in the whole world in the next decades. Yeah. And what's your prognosis for in 1,000 years?
Yeah, I think first, just to continue the 100 years, because I think one thing that will push us is the space exploration. In space exploration, they are working in NASA and ESA and different parts of the world are working very hard at the moment to have a base on the moon. And I believe we will have a base on the moon, let's say in 10 years from now. And then we need to find a way to go underground in these very dangerous places. free radiation and all these other challenges, then we need to have autonomous systems much more in place. And then it will push the development of this thinking of data-driven systems, autonomous system, much harder. Yeah, and I really believe in 1,000 years from now, we will be an interplanetary species that have gone underground on a lot of planets using data-driven systems and autonomous operations of underground construction.
Yeah, absolutely. I think in 1,000 years, I hope we are interplanetary then. And of course, there we will go underground. We have to do that. But I'm also curious how it is here on Earth if we still have that high need to go underground. Let's see about that. Tom, thank you for the very interesting talk. I think this was a very nice conversation about rock mass classification. And I thank the listeners for hanging with us here, and see you next time on the NGI Technical Podcast.